Okay, so here we are at the final section of the semester. And we are still talking about Taylor series. Now we're just going to show in a couple examples how we can use Taylor series to approximate functions. Because ultimately that is what the idea is, right? Is to take a given function and write out the first few partial sums of its Taylor series instead. Because then effectively what we're doing is we're replacing the function, which might be complicated, with a polynomial, which is always going to be easier to work with. Even if the effort taken in computing that polynomial in the first place seems like a lot, down the line, guaranteed it's going to be more efficient. Well, maybe. So basically, all that we're doing in this section is we're just going to have a few applications of Taylor's inequality. So we're going to be using Taylor's inequality to get some error estimates for approximations. Okay, so first off, approximate the function, the third root, by a Taylor polynomial of degree 2. So of degree 2, so that means we only need to take 1, 2, 3 terms to get to the degree 2 term, centered at 8. So since we need a polynomial of degree 2, we only need the first 3 terms of the Taylor expansion. Okay, so let's compute the coefficients. So c sub 0, well, that's the value of the function at the center point. So that's the cube root of 8. So that's 2. Okay. Next, we have to start taking derivatives. So this is x to the power 1/3. So 1/3 minus 1 is minus 2/3. So that means c sub 1 is f prime at 8. So that's 1/3, 8 to the negative 2/3. Let's see, so the third root gives us a 2. 2 to the negative 2 is 1 over 2 squared. So that's 1 over 4. So 1/3 times 1 over 4 is 1/12. Okay, next we take the second derivative. And at this point, we don't need to go any further. So bringing down that, we get negative 2/9 x to the negative. So subtracting 1 again, that is minus 5/3. So c sub 2 is going to be f double prime at 8 f double prime at 8 over 2 factorial, which is just 2. So let's see. So we have minus 2/9. So this 2 and this 2 are going to cancel each other. Uh, 8 to the negative 5/3. So the third root again is 2. So 2 to the negative 5 is 1 over 2 to the 5th. So that's 1 over 32. So 9 times 32 is 288. Okay, so with the coefficients in hand, we can now compute the desired Taylor polynomial. So the approximation is 2 plus 1/12 x minus 8, right? Because the center point is at 8, minus 1 over 288 x minus 8 squared. Okay, so that's the approximation of the third root by a quadratic. And this approximation is valid as long as x is close to 8. So the next question is, how accurate is this approximation when x is close to 8? Specifically, between 7 and 9. So notice this is an interval which is centered at 8. So to get this, so the alternating series theorem isn't going to work because this isn't an alternating series. It's positive, positive, minus. So we're going to have to use Taylor's inequality here. So let's see, what are the ingredients in Taylor's inequality? So, so we are looking to compute r sub 2, that is the remainder upon taking the, right, that's the difference between the actual function and the second degree Taylor polynomial, which is what we're doing here. So we're looking at r sub 2. Now, what is the range of x's? Well, x is between 7 and 9. So that's the same as saying that the distance between x and the center point 8 is less than or equal to 1. So right? That's equivalent. Because remember, absolute value x minus 8, this is the distance between x and 8. And since x is inside this range, the distance between x and 8 is never going to be any greater than 1. So that's this filled in. So a is equal to 8, d is equal to 1. K is equal to 2. What other ingredients do we need? So the only other ingredient that we need is this bound. So this is going to be a bound on the k plus 1th derivative. So since k is equal to 2, that's going to be a bound on the third derivative. So let's see, what is the third derivative? So over here, we computed the second derivative, so let's just go one step further. So bringing down the negative 5/3, the negative cancels. So 2 times 5 is 10. 3 times 9 is 27. Negative 5/3 minus 1 is negative 9/3. Oh, 9/3, well that's the same as 3. Wait a minute. No, I'm sorry. I'm sorry. Negative 5/3 minus 1 is negative 8/3. That's right. Because we're subtracting 3 from the numerator. Okay, so what is a bound on this guy? Well, what is this function doing? What does this function look like? I mean, we got 10 over 27, which, whatever, that's a constant. But this dude here, being a negative power, this is a reciprocal. Now, x to the 8/3 is an increasing function, right? any power function like that is increasing. So that means the reciprocal is going to be decreasing. Well, we want to find an upper bound on it. So we want this guy to be as big as possible. So for this guy to be as big as possible, because this is decreasing, we need x to be as small as possible. So, so x to the negative 8/3, the reciprocal, will be as big as possible when x is as small as possible. So, in the range that we are considering, the smallest that x could possibly be is 7. So we will get our upper bound when we just plug in x equals 7 here. I guess these parentheses aren't necessary. So let me just go ahead and throw that into the calculator and see what it gives us. So we get around 0.0021. So that's going to be our m. Okay, so now that we have all the ingredients, let's plug this into Taylor's inequality. So the remainder upon taking the Taylor polynomial of degree 2 is guaranteed to be less than or equal to all of this junk. So m sub k is this. And I'm just going to recompute it so that I get rid of the rounding error. Yeah, actually, yeah, I'm gonna hold off on computing it until the end, because otherwise there's going to be some round off error happening. D is equal to 1 in this case. K is equal to 2, so k plus 1 is 3. Not that it matters, because 1 cubed is still 1. 3 factorial. Okay, so now let's throw that into the calculator. And I get so around there. So that's about how accurate this approximation is going to be. So in particular, you're not going to start noticing the error until you get down to like the 4th decimal place or so. Maybe the 3rd decimal place. Okay. So down here, we are taking the sine function and we are replacing it with the first 3 terms of its Taylor expansion. So remember, the Taylor expansion for sine is just, it's alternating. We've got the factorials of odd numbers on the bottom and only odd powers. So this is just the first 3 terms of the Taylor expansion. And we are restricting ourselves to values of x between negative 0.3 and 0.3. So what is the maximum error possible in using this approximation? Okay, well, in this case, we could use the alternating series approximation theorem, because the expansion for sine x is alternating. So in particular, the alternating series theorem tells us that if you take the first term, then the error is going to be bounded by the second term. If you take the first two terms, then the error is going to be bound by the third term. If you take the first three terms, which is what we're doing, then the error is going to be bounded by the fourth term. So what's the fourth term in the expansion? In absolute value, right? Because you're neglecting the alternator. Right? That's part of the theorem. Okay, so we do have to be a little bit careful here, because in the alternating series estimation theorem, it must be the case that when you neglect the alternator, the terms are positive. But that's not necessarily happening, because x might be negative here. But here's the thing. This function is odd. This function is odd. So what's happening when x is negative is a reflection of what's happening when x is positive. It's a perfect reflection. So let's just assume that x is positive and go from there. So the error is going to be bounded by the next term in this sequence, which would be x to the 7 over 7 factorial. Now, since we are assuming that x is positive, the largest that x can possibly be is 0.3. So this is going to be less than or equal to 0.3 to the power 7 over 7 factorial, which is about, well, let's see. Oh, that's a power of 8 there. Okay. Okay. So that's the worst that the error can possibly be in this range. And that's the case if x is positive. If x is negative, well then the sign of the alternators is just going to flip, because then this guy is going to be negative, so this becomes positive. This becomes negative. So it's still an alternating series. Right. And because it's just opposites, everything's going to work out exactly the same. So okay, yeah, it's fine. It's fine. Don't worry about it. I don't know. It's a little bit sloppy, but The book doesn't really go into any greater detail than that. In any case, moving on. Use this approximation to find the sine of 12 degrees, correct to 6 decimal places. Well, let's see. Sine of 12. So I don't know why he decided to put degrees in here. I guess just because people still use degrees in engineering and whatever. So remember, to convert degrees to radians, you just have to multiply by pi over 180. So that's the same as pi over 15. Yeah, that's pi over 15. So, is this within our range? So we're looking at values between negative 0.3 and 0.3. Pi over 15 is that's about 0.2. So that's within the zone that we are considering. Okay, so all we need to do then is just plug this into the approximation, and the error is guaranteed to be smaller than whatever times 10 to the negative 8. So certainly then it's going to be correct to 6 decimal places. So certainly the polynomial approximation above will give us the desired accuracy. So just plug pi over 15 into this dude and see what we get. I will say, it feels slightly disingenuous to be going through all of this and then end up plugging things into the calculator anyway, because like, just plug it in, just do this. Just plug this into the calculator into the first place. It's like we're not really gaining anything by doing this, but it serves at least as an illustration of how one might use Taylor series to replace functions. So imagine that this wasn't sine, right? This wasn't something that a computer can easily compute. Imagine that this was the Bessel order of the 15th kind of degree 11 billion. You know, imagine that as something weird and wacky. Well, then certainly replacing it with a polynomial is going to be more computationally efficient. We're just using sine here instead of something complicated as a way of illustration. So yeah, in reality, instead of doing this with sine, we would be doing it with something much crazier. Anyway, what does this give us? So this gives us about 207,912. So there's the 6 decimal places that they asked for. And finally, okay, so we know that the error is going to be on the order of magnitude of like 10 to the negative 8 if x is between 0.3 and 0.3. For what values of x is the approximation accurate to within this? So this is less, right? This is smaller than something times 10 to the negative 8. So we would expect that the accuracy would be even bigger, right? We would expect that we would get an even bigger effective range if the error that we're looking for is smaller. So let's just see if that is indeed the case. So we already know that the error is going to be bounded by x to the 7 over 7 factorial. So basically, we just need to set that less than or equal to this, and then solve for it. So let's just solve this inequality for x. And indeed, that's not too hard. Just multiply both sides by 7 factorial, and then take the 7th root. So what do we get? Okay, so as expected, we do get a larger number than 0.3. So we get a wider range of acceptable x's for the approximation. So let's not lose track of what we're doing. We're talking about the accuracy of this 5th degree polynomial for sine. So the given polynomial is an accurate approximation for sine x to the desired accuracy for values of x less than or equal to, well, between negative 0.8218 and positive 8.8218. And again, that's because this dude is an odd function. So whether you're in the positive range or the negative range, the picture is exactly the same. It's just a reflection. So it's not a big deal. Okay, so that's about all there is to say about this one. Either use Taylor's inequality to obtain your error bound, or use the alternating series approximation theorem to get your error bound. And then, aside from that, really just focus on what they're asking you for and go from there. So, that's it. I hope to see you all in the Collaborate sessions for review.